So we have in problem 1, which goes as follows. We have this region, cylindrical volume of magnetic field as shown. Cylindrical volume in which there is magnetic field as shown. R is the radius of this cylinder. This is the cross section of the cylinder. And this is a time varying magnetic field. It's given that it's a time varying magnetic field. B is given as B naught T. B is given as B naught T. That's the time varying magnetic field going into the plane of the board, right? So in this region, at a distance small r, the electric field will be perpendicular to that small r, and the magnitude of the electric field will be given by small r by 2 dB dt at any r, small r, right? So at any given r, the electric field at a distance small r from the center O is going to be given by r by 2 dB dt, which is like r by 2 B naught, which is like r by 2 B naught. That's the electric field at a distance small r, right? At a distance small r, and it will be perpendicular. So if O is the center and I take a point P at a distance small r, then the electric field will be perpendicular to the radius at that point, E at small r, and would be of magnitude B naught r by 2, right? Anywhere in this region at a distance small r from the center of the symmetric region. Clear? Now, what they say is there is a rod kept in this region, a rod AB placed in this region, right? I want to be able to calculate the induced EMF in the rod AB. Let's see how to handle this. Okay, in this case, different points on AB are at different distances from O. So the electric field from A to B is not uniform, because different points on AB are at different distances from the center. So they would subscribe to different values of the electric field. Not only will the electric field between different points in this region is different in magnitude, but also different in direction, because at any given point the electric field will be perpendicular to the radius at that point, right? So then, to look at things independently, this is the center O, this is the rod AB, all right, and say the distance of the rod from the center O of this region is D, right? Now if I look at a point P of this region, point P of the rod, which is say at a distance small r from O, different P's will have different values of small r and will have different values of theta, different values of small r and different values of theta. Now the electric field at P is going to be what? The magnitude of the electric field is going to be B naught r by 2, right? And will be perpendicular to this r. So the electric field at this point is going to be perpendicular to this and would be equal to B naught r by 2, is going to be B naught r by 2. That's going to be the electric field at a distance small r from O, right? Now check that this electric field E, if this is theta, this is 90 minus theta, so this is theta, right? This is theta. See that? This electric field will have two components, a component E cos theta along AB and a component E sin theta perpendicular to AB. E sin theta perpendicular to AB will not drop EMF across AB, right? Whereas E cos theta, which is along AB, will drop EMF across AB, yes or no, right? So E sin theta, which is perpendicular, will be passive. It will not drop EMF across AB. Whereas E cos theta is that component of the electric field which will drop potential across AB and will therefore produce EMF, right? So at every P, I will have to look at E cos theta at that P, right? That's what, isn't it? Which means, say at a given P, which is at a distance small r, I look at E cos theta, right? Then what is this E cos theta? What is this B naught r by 2 cos theta? B naught r by 2 cos theta. That's a component of the electric field which is participating in producing EMF in the rod AB. Now, what is small r cos theta? Small r cos theta is D, which is the same for all P's. Small r cos theta is D, which is the same for all P's. Yes or no? So, this is like B naught by 2 into D. See, this is small r. Small r cos theta is D, the perpendicular distance of O from this rod. Right? Yes or no? Which means, even though the electric field from A to B is varying both in magnitude and direction, but the component of the electric field along AB is the same. The component of the electric field along AB is the same and is equal to B naught by 2 into D, where what is D? D is the perpendicular distance of the center from the rod AB, which is the same no matter where I choose my point P. Yes or no? Isn't it? Now, having said this, then life becomes very simple. From A to B, all that I have to take care of is a uniform electric field along AB, which is like B naught D by 2 is a uniform electric field from A to B along AB, right? And if I have to find the potential that a uniform electric field drops from A to B, it's going to be EAB into the length AB is the potential that drops, will be the induced EMF, right? So the potential that drops from A to B and is also the induced EMF across AB is actually EAB into the length AB. EAB into the length AB, right? The length AB is given to be how much? 2L. The length AB is given to be 2L. The length AB is given to be 2L. So then, can I remove the clutter from here? Have you registered these thoughts? Okay. So, the EMF across AB in the rod AB is EAB, which is B naught by 2 into D into the, this is that EAB, B naught by 2 into D into the length AB, which is 2L, right? Now, what is D? This is D. If capital R is the radius, this is L, this is L, this whole length is 2L. So then realize D would be root R squared minus L squared. So induced EMF across AB is B naught L into root R squared minus L squared, plugging in D as obtained from Pythagoras theorem. That's the induced EMF in the rod AB. Got me? Let's look at the next problem.
So what if the region was not cylindrical but something else like a cuboid or something?
Okay, now if the region was cuboid, then also you could imagine, see this result is true only for cylindrical region, because then there is tangential electric field, otherwise the electric field would be a lot more complex, right? So this result that I have derived, there would still be an induced electric field, but it will not be as simply obtainable, right? In problem 2, there is a vertical conducting ring of radius r. Vertical conducting ring of radius r falling vertically with a speed v, falling vertically with a speed v in a horizontal uniform magnetic field everywhere. Can you tell me if there is any induced EMF in this? There will be. Is the flux associated with this changing with time? If it's falling. If the flux associated with this is not changing with time, there is not going to be an induced EMF. There won't be a current driven through this loop, clockwise or anti-clockwise, right? Isn't it? There won't be any current driven through this loop because the flux associated, when it falls, the flux remains the same. B into this area, neither B is changing nor area is changing. That's going to be the same, right? Imagine this rod CD. Imagine this, let's say, imagine this to be a rod CD. B is into the plane of the board. V is like this, right? So, V cross B is lateral. There is no component of V cross B along CD. There is no component of V cross B along CD. Do you realize that? V is like this, B is like this. So, V cross B is lateral. No component of V cross B along CD, right? And therefore, if there is no component of V cross B along CD, that means the EMF across CD must be 0. Potential drop across CD must be 0, isn't it? Is it or is it not? That means C and D must be at the same potential. C and D must be at the same potential. However, if you imagine a rod AB like this is V, then A and B will not be at the same potential because there would be V cross B towards B, causing B to be at a higher potential compared to A. There would be a potential drop across AB. Right? A question that you would have to answer. Let me see if you could figure that out. A and B are not at the same potential. C and D are at the same potential. But if A and B are at different potentials, why is it that there is no current driven through the loop? Think about that. Okay. For sure there isn't going to be a current because there is no induced EMF. Why is there no induced EMF? Because the flux associated with the loop is not changing with time. That's fundamental. That's cardinal. That's godly. Okay. But for sure, from a V cross B consideration, you find that A and B are at different potentials, C and D are at the same potential. But if A and B are at different potentials, why on earth is there no current driven through the loop? Think about it. Okay? Let me get to the next problem. Problem 3. But so far so good, right? No current, no net induced EMF in the loop. Fine? Can I wipe this off? See, why do I look at V cross B? Because the direction of V cross B will give me the point which is at a higher potential compared to the other one. So, in this case, there is no component of V cross B along CD. So, neither C nor D is at a higher potential. They are at the same potential. So, there is a semicircular loop, say PQ, which is hinged at P, and is in a state of pure rotation about P with an angular velocity omega, I hope you understand that. It's like this. This entire thing is rotating with an angular velocity omega. This is a rigid wire. PQ, hinged at P, maintaining its shape, but is rotating about P with an angular velocity omega. Clear? We want to find the induced EMF across PQ. Like I mentioned to you at the very onset, I could replace this with a straight wire PQ. This could be replaced with a, for the sake of calculation of the induced EMF, I could replace it with a straight wire PQ hinged at P, having an angular velocity omega. The length of this would be 2r, twice the radius. So the induced EMF is going to be how much? Half B omega 2r whole squared, yes or no? Half b omega 2r whole squared, that's going to be the induced EMF. So induced EMF is going to be b omega is going to be twice b omega r squared. Twice b omega r squared is going to be the induced EMF. Right? The sense of this, which would be at a higher potential, P or Q. So imagine a segment like this, it has a velocity this way. So V is like this, B is going into the plane of the board, so V cross B is towards Q. So Q would be at a higher potential compared to P. Right? So in this, you can electrically have a battery of this kind, where the positive terminal connected to Q, negative terminal connected to, and this is like a induced EMF. Right? So there is a conducting plane. This is a conducting plane, right? This is a conducting plane. And there are two spheres on this conducting plane. There are two spheres on this conducting plane. Sphere A and sphere B. This is in a state of pure rolling. Is in a state of pure rolling with the center of mass having a velocity v, and therefore if it's in a state of pure rolling, then the angular velocity of this must be v by r. Yes or no? Angular velocity must be v by r if it rolls without slipping on this conducting plane. Same with this. This has a velocity v this way and has an angular velocity omega like this. Pure rolling, where again omega would be v by r. Why? Because it's rolling without slipping. I hope you've not forgotten rolling without slipping. Right? Now, what we want to do is, say there is a point P1 here and there is a point Q1 here. The top and bottommost point of this. And there is a point, say P2 here and a point Q2 here. I want to find the potential difference between P1 and P2, between their topmost points. I want to find the potential difference. Clear? Now, look, if it's rolling without slipping, it really means that this point Q1 is at rest. It must be the instantaneous center. I could imagine this to be in a state of pure rotation about Q1. I could imagine this to be in a state of pure rotation about Q1. So I could replace this unit, say, by a P1 Q1, in a state of pure rotation about Q1 with an angular velocity omega, isn't it? About the instantaneous center. The whole rigid body could be imagined to be in a state of pure rotation. Isn't it? Now, this length is 2r. So the induced EMF across P1 Q1 is going to be what? Half b omega into 2r whole squared is the induced EMF across P1 and Q1. Now which one would be at a higher potential? If say the velocity of a given segment is say v1 like this, right? So v1 is this way, b is into the plane of the board or out? It's going into the plane of the board. Okay, so if it's going into the plane of the board, then v is like this, b is like this, so v cross b would be downwards. V cross b would be downwards. See, v is like this, b is like this, so v cross b would be downwards. From v to b, it goes down. B is like this, from v to b, this will go down. V cross b, right? So q would be at a higher potential compared to Q1 would be at a higher potential compared to P1. So then, can I say that potential at Q1 minus potential at P1 must be half b omega into 2r whole squared, which is 2b omega r squared. Yes or no? Where if I replace omega by v by r, replace this omega by v by r, this becomes 2b vr is vp1 minus vq1 minus vp1, right? Now that's as far as p1 q1 is concerned. Now as far as p2 q2 is concerned, look at p2 q2. So this is p2, this is q2. I can again imagine this to be in a state of pure rotation about q2 with an angular velocity omega, and the induced EMF across p2 q2, the induced EMF across p2 q2 would be the same in magnitude, right? But which one would be at a higher potential? V is like this, say v1, then v1 b, v1 cross b would be upwards, so p2 would be at a higher potential compared to q2, so vp2 minus vq2 would have the same magnitude. 2bvr will be 2bvr, yes or no? Same calculations, imagining it to be in a state of pure rotation about q2 and p2 being at a higher potential compared to q2, so I have two conditions. This is 1 and this is 2. What I am seeking is vp2 minus vp1. vp2 minus vp1 is what I am seeking. Now tell me, between q1 and q2, what's the potential difference between q1 and q2? 0. Why? Conducting plane, absolutely, and there is no current. So q1 and q2 must be at the same potential. So vq1 is vq2. These are points on the conducting plane in which there is no current. If there was a current, there would be potential drop. There is no current, potential difference is 0. So vq1 is vq2. So if I add equations 1 and 2, then I get vp2 minus vp1 is 4 bvr. Right? Problem 5 is very much like an earlier problem. There is a conducting ring of radius r with a conducting spoke is in a state of pure rolling. That means v and omega, which is going to be v by r for the sake of pure rolling. In a uniform magnetic field, it's dots now, so coming out, there is B coming out, we want to find V0 minus VA. Again, I can imagine this OA to be in a state of pure rotation about A with an angular velocity omega, right? If r is the length, then realize that if this is the velocity of this, v is like this, b is like this, so v cross b would be towards A. So A would be at a higher potential compared to O, right? Isn't it? So then, can I say VA minus VO is going to be half b omega r squared? R squared, where omega I can write as V by R. Half BVR. So that's VA minus V0. And V0 minus VA therefore would be minus half BVR. Minus half BVR. Clear? Alright. Let's look at the next problem. Simple, isn't it? Can I wipe this off? Problem 6. We have a rod of length L having uniform charge Q distributed. So let me not call it, say LM then, because Q is the charge distributed. Q is the charge distributed is rotated about one end with frequency f. That means with angular velocity 2 pi f. With angular velocity 2 pi f, right? We want to find its magnetic moment. We want to find its magnetic moment mu. Now, what is its angular momentum about L? Angular momentum about L, the fixed end, is I, which is 1/3 ml squared into omega, small l squared into omega. And we already know that mu, the magnetic moment divided by the angular momentum, which is 1/3 ml squared into omega, must be the gyromagnetic ratio, q by 2m. And then mu is therefore available from these considerations. You don't have to obtain it from first principles. Just use the gyromagnetic ratio for all cases, q by 2m, right? So mu is obtainable. Let's look at problem 7. Can I wipe this off? So in problem 7, we have a situation like this. There is a rod, say PQ, and there is a region of, this entire thing is a region of uniform magnetic field B going into the plane of the board, and this is initially at rest at time t equal to 0. Its velocity is 0, and it's being pulled with a force F. Say M, and M is the mass, L is the length of this connector PQ. Okay. Let's start figuring out the physics of this situation. Okay. Now at time t equal to 0, this has no velocity, so there is no motional EMF in BV. If there is no motional EMF, there would be no current, there would be no magnetic force. The only force acting on the connector is F. So initially at time t equal to 0, it has an acceleration which is F divided by m. Right? Yes or no? Now when it's pulled to the right, this acceleration leads to build-up of a velocity. Build-up of a velocity, right? So t seconds later, say PQ comes here. T seconds later, PQ comes here, and PQ would have developed a velocity v. PQ would have developed a velocity v. Now it's a moving conductor in a magnetic field. There is going to be a motional EMF. V is like this, B is into, so V cross B would be towards P. So there is going to be across PQ at an instant of time t across PQ. There is going to be a motional EMF epsa, which is BVL, where P is at a higher potential compared to Q. Right? There is going to be a motional EMF. Now this motional EMF will drive a current in this I. This way. This is the sense of the current driven. Therefore, there would be I, which would be BVL by R. BVL by R is the current driven through this. Now we have a current carrying conductor exposed to a magnetic field. A current carrying conductor exposed to a magnetic field will experience a force, a magnetic force, right? My DLs, R is this way, DLs are like this, B is into, so DL cross B would be this way, leftwards. So then a magnetic force which is BIL, a magnetic force FM which is BIL x to the left, right? Now BIL means I is BVL by R. So replace this I by BVL by R. You get this magnetic force as B squared L squared. V by R is the leftward magnetic force, right? There is already an external force F acting. There is an external force F acting. Now the acceleration therefore must have decreased because of this retarding force. The acceleration must have decreased. What's the acceleration of the connector in this state? F minus B squared L squared V by R divided by M is the acceleration. So what's happening to the acceleration? It's decreasing. Because V is growing, acceleration is decreasing with time. Yes or no? Acceleration is decreasing with time. So even though the velocity is increasing, it's increasing at a decreasing rate. Because acceleration is decreasing. If in the first second the velocity is increased by 1 meter per second, then in the next 1 second it will increase by less than 1 meter per second. It's still increasing, but at a decreasing rate. You know what I'm saying? So what you would expect out of this physicality is the following. The velocity increases, but at a decreasing rate. So in this case, the velocity is increasing, but acceleration is decreasing. The velocity is increasing because there is a rightward acceleration, right? But that acceleration is decreasing. So you would expect the velocity time graph to be at time t equal to 0, it starts from rest. There is an acceleration, but the slope dv dt must decrease because the slope of this represents the acceleration. Velocity then increases, but less and less rapidly. It increases, but less and less rapidly. Do you realize that? Eventually, what's going to happen is, since the magnetic force is growing, the external force is remaining constant. So at some point of time, you would expect the magnetic force to match the external force. The acceleration will become 0. Once the acceleration becomes 0, velocity will become constant. And that velocity is the terminal velocity of the connector. That velocity is the terminal velocity of the connector. This velocity is the terminal velocity. Eventually, it approaches this velocity. At time t equal to infinity, it approaches a terminal velocity, which is the steady state velocity of the connector, which is the steady state velocity of the connector. And when does that happen? That happens when the external force balances magnetic force. So acceleration becomes 0. So when the acceleration becomes 0, this V will become V terminal. V will become V terminal, right? So then V terminal can be obtained when I say F minus B squared L squared. This V will become V terminal by R. This is 0. For V equal to V terminal, acceleration will become 0. So V terminal can be obtained. This happens after a very long time. We say mechanical steady state conditions have been obtained in the circuit, right? Now look at the power. Can I wipe this off? The power associated with the circuit. That means the power that this force is providing. The power that this force is providing is F into the velocity at that instant. That's the power that it's providing, right? Where does this power go? This is the power it provides. It goes towards two things. One part of this power takes care of the joule heating I square R at that instant. I square R watts is consumed at an instant when the current through the resistances are. Where does that I square R come from? It comes out of a partial consumption of F into V. This power, these many watts is what is coming into the system, right? F into V. And where does the rest go? The rest goes towards change of kinetic energy of the rod. This power that you are providing to the rod, goes gets delegated into two fronts. One part of it gets consumed towards joule heating. The rest goes towards change of kinetic energy. You know what I'm saying? Right? Now, when see this V equal to V terminal is steady state for the system, mechanical steady state for the system, right? Now, once steady state conditions are attained, then the velocity does not change after that. Velocity remains V terminal. That means no part of the external power goes towards change of kinetic energy. Then the external power F into Vt is entirely consumed in joule heating of the resistance. That's all. Right? That's under steady state conditions. Initially, at time t equal to 0, there was no current. So all the power, there was no power, of course. F, velocity was 0. As you go on increasing the velocity, there is power getting delegated, partly into joule heating, partly into increase of kinetic energy. But kinetic energy is increasing at a decreasing rate. Right? So less and less of power given to the system is consumed towards change of kinetic energy. More and more gets delegated towards joule heating. Do you all understand this? Now, what is happening to dV/dt? It's decreasing. Do you realize that? At any given time, this slope of this will give me dV/dt. Slope of this tangent will give me dV/dt. That's the acceleration at that instant, right? What's happening to dV/dt? It's decreasing. Do you see that? dV/dt is decreasing. So acceleration is decreasing with time. Right? So let's see the rate at which power is being supplied by this external force. This is the rate at which power is being supplied by the external force. That must be F into dV/dt. Right? That means F into acceleration A. But A is decreasing with time. So dP/dt is decreasing with time. So dP/dt decreases with time. Rate at which power is supplied is decreasing with time. Right? Hey, if there is a uniform magnetic field, there is a rod of length L exposed to a uniform magnetic field oriented anyway, right? And say V is the velocity of the rod, then if B is uniform, then the EMF generated across the rod is given by V cross B dot dl dot dl dot dl dot L eventually. That's the EMF generated across the rod, right? That's the motional EMF in the rod, V cross B dot L, right? In the given problem, B is given to be 3I plus 4J plus 5K. That's B. A rod of length 5 meters is placed along the y-axis. This is parallel to the y-axis, so the L is 5J cap is L for the rod, 5 units parallel to the y-axis. So the length L of the rod is vectorially represented as 5J cap, right? And the rod is moved parallel to the x-axis. With a velocity 1 meter per second. That means V would be I meters per second. I cap meters per second is the velocity, right? So all that you need to do is V cross B dot L. Hey, do you realize this is scalar triple product VBL? So all that you need to do is carry out this operation to find the EMF generated across the rod. Scalar triple product of VB and L. Right? Well, you have a question? No? Can I wipe this off? There is a resistance R. There's a connector. Magnetic field B. And by some means, this connector is moved with a constant velocity V naught. Say the connector is moved with a constant velocity V naught. These are two parallel conducting smooth rails. Uniform magnetic field perpendicular into the plane of the board. There is a resistance R between the two ends of the rail. Which of the following are correct? Okay, there is an external agent pulling it with a constant velocity V naught, right? If he's pulling it with a constant velocity V naught, if an external agent is pulling it with a constant velocity V naught, that means no part of the power that the external agent is supplying goes towards change of kinetic energy. That means F external into V naught goes where? Completely into Joule heating. Completely into Joule heating. So the thermal power dissipated here is entirely at the behest of the external power provided by the source. Why? Because no part of the external power F external into V naught goes towards change of kinetic energy of the rod, right? So option A, the thermal power dissipated in the resistor is equal to the work done by the external person pulling the rod. Yeah, right. All the work he is doing is going only towards dissipating energy here, and none of it contributes to change of kinetic energy. Clear? That's option A. So option A is right. Option B, if external force is doubled, then part of the external power increases the velocity of the rod, right? A certain value of external force will maintain V naught, because then it's just enough to take care of the power dissipated. But if you double this, then part of the kinetic energy of this will increase. Kinetic energy of this will increase. That's so option B is right. Option C, Lenz's law is not satisfied if the rod is accelerated by external force. God bless you. Lenz's law is always satisfied, right? There is no question of buying this. Lenz's law will be satisfied. Okay. If the resistance R is doubled, then the power required to maintain a constant velocity becomes half. Hey, now again, if I want to maintain constant velocity, that means I'm not changing the kinetic energy of the rod. So what would I require in the resistance? Epsilon squared by R. Epsilon is the EMF available in the circuit. What's the EMF available in the circuit? Plus minus. The EMF available in the circuit is BV naught into L. V naught is not changing with time. So epsilon is not changing with time. Epsilon is not changing with time. So if you double R, the power becomes half. The power becomes half, because epsilon is not changing with time, right? So option D is right. Option D is certainly right. Have I done 10 in the class? Something like 10? No? Mutual inductance, if there is a longer... No? Okay, how does it matter? I'll just do it again. Can I wipe this off? Problem 10. There is a very long thin wire placed in the XY plane such that the length A of the loop is parallel to the wire. It's a current carrying wire carrying current I. The length A of the loop is parallel to the wire. Width B. The distance between the wire and the nearest edge is D. I want to find the mutual inductance of the system. To find the mutual inductance, I would imagine current through the bigger one and flux through this. Then flux through this divided by I through this will give me the coefficient of mutual inductance. So what I do is, this is a non-uniform magnetic field, right? I imagine, say, a strip of this kind. imagine a strip at a distance x from this wire and of thickness dx. All points on this chosen strip will be at the same b. How much? Mu naught I by 2 pi x. So b at every point of this is going to be mu naught I divided by 2 pi x is the magnetic field at every point of this. B at given x. Right? So the flux associated with this is going to be A into dx is the area of this strip. A into dx into B will give me the flux associated with this. So the flux associated with the chosen element is going to be B at x, which is mu naught I by 2 pi x into A dx. A into dx is the area of the shaded portion. So the total flux is going to be sum of all of this, where x runs from D to D plus B. X runs from D to D plus B. That's the flux phi, which then when you integrate is like mu naught I divided by 2 pi log B plus D divided by D. B plus D divided by D. So phi divided by I is mu naught by 2 pi log B plus D by D. That's the coefficient of mutual inductance. Coefficient of mutual inductance is phi divided by I, which is mu naught by 2 pi log B plus D divided by D. That's the coefficient of mutual inductance of this pair. Right? Oh, I missed out an A because I missed out an A here. Alright, so M proportional to A. That's all that could be said. M proportional to A. It can never be proportional to current, because when I divide by current, I am killing out the current. For all currents, M will have the same value because I am only imagining I and the corresponding phi. So phi by I ought to be a constant inherent property of the pair. It will not depend on the current. If the current changes, phi will change such that phi by I will be maintained constant, the coefficient of mutual inductance, right? Okay, let's look at the next one then. Simple, isn't it? Eleven. So we have a relatively small loop, coaxial, with a much bigger loop. This is of radius r. This is of radius small r, where small r is much smaller compared to capital R. Loop A moves towards loop B with a constant velocity v. What is the distance between the two loops x when the induced EMF in loop A is maximum? So that means we'll imagine current through this and flux through this, so that the flux through this varies while it's moved towards this and causing an induced EMF in the smaller loop. Right? We want to find the separation between their centers, say x, for which the induced EMF is going to be the maximum in this loop. Right? That's the problem. Okay. Now, look, small r is much smaller compared to capital R. Right? So this I produces a magnetic field at the center O of small r. What's the magnetic field produced at O by this? Magnetic field produced at O is going to be mu naught I r squared divided by 2 r squared plus x squared to power 3 by 2 is the B naught produced. Now, since this is really small compared to this, I can imagine all points on this to be really close to O. Therefore, this could be imagined to be a region of uniform magnetic field, where magnetic field is the same as the magnetic field at the center O, and all the field lines being axial. That means hitting the loop normally. Right? So the flux associated with this is going to be B naught into pi small r squared is going to be the flux associated with this. Right? So the flux associated with the smaller loop A is going to be, say, mu naught I r squared divided by twice r squared plus x squared to power into pi r squared. Got it? Now the induced EMF is going to be d by dt, right? Can I remove this from here? Induced EMF is going to be d phi dt, or magnitude of this, right? So if I differentiate this with respect to time, see, all of this mu naught I squared 2 pi small r squared, they are all constants, right? They are all constants clubbed together, right? And when I differentiate this, then I get like a minus 3 by 2 r squared plus x squared to power minus 5 by 2 into 2x into dx dt, which is v. Into dx dt, I'm differentiating with respect to time. All of this is with respect to x, and then x with respect to time will give me v. Yes or no? Right? Now v, of course, is constant, not varying with time. This minus 3 by 2, etc., all of it is constant. So this essentially is like some constant c, say x into r squared plus x squared to power minus 5 by 2. This v minus 3 by 2, all of this put under c. Right? That's going to be the induced EMF. Now we want to find out the value of x for which epsilon is the maximum. D epsilon dx must be 0 for epsilon to be maximum. D epsilon dx must be 0. Right? So for epsilon to be epsilon max, d epsilon dx is 0. And d epsilon dx will give me like constants all put together, derivative of this into this, which is like a r squared plus x squared to power minus 5 by 2, right? Minus 5 by 2 r squared plus x squared to power minus 7 by 2 into 2x into x, so into 2x squared is what I get as d epsilon dx. This is all d epsilon dx, right? See, just differentiated, nothing else. Can I just remove this from here? Which means, say I took r squared plus x squared, all of this there is a constant, to power minus 7 by 2 common from this. So I get like a r squared plus x squared minus 5 into x squared, because this 2 will get cancelled. This must be 0. Right? Which would give me this equal to 0. That means r squared minus 4x squared must be 0, or x must be r by 2. At x equal to r by 2, epsilon would be Yes or no? Got me? Okay. Let's look at the next problem. এই মালটার খুন করে দিতে হবে. Can I wipe this off? Okay, problem 12. A long straight wire is placed along the axis of a long circular ring of radius r. This is a long straight wire placed along the axis of a long circular ring of radius r. This is a circular ring of radius r, and we have this wire. And we want to calculate the mutual inductance of this system. We want to calculate the mutual inductance of this pair. Okay. Now, I would obviously imagine a current through this and calculate the flux through this. Now, this current carrying wire, as you realize, produces at every point of this loop a magnetic field which is this way along the tangent, isn't it? If I look at some other point, say some other point P, then I would imagine, let's say, a circular loop like this. Then at this point P, the magnetic field produced would be this. So which means one thing is guaranteed. Have I confused you? Sneha, see, if there is a current carrying wire like this, then if you look at this is a current carrying wire, right? If you look at a certain point P, say a point P here, okay, what's the magnetic field that it produces? Mu naught I divided by 2 pi, and what's the direction of the magnetic field? Going into, right? Going into. Now, if you think of it, if it goes into, and this is the plane of the loop, do you realize that P into would actually lie in the plane of this loop? See, at this point, it's going to be like this, like this, like this, tangential at every point. So, the different B's that I'm producing on this circular loop, every point inside and on the circular loop would be in the plane of the circular loop. All the B's that will be produced would be in the plane of the circular loop. Yes or no? Are you there with me? The B's produced at every point here would be in the plane of the loop. Would be in the plane of the loop. At every point they'll be perpendicular to R, but would be in the plane of the loop. Right? That means if all the B's here are in the same plane, then there is no B passing perpendicular to the plane. There is no B passing perpendicular to the plane of the circular loop. So what's the flux associated with the loop? 0. The flux associated with the loop then, because of this current, is going to be 0. So the coefficient of mutual inductance of this pair is going to be phi divided by I, which is going to be 0. So coefficient of mutual inductance is 0. So now, which means if you vary current in this, there would be no induced EMF in this, because the flux through this is remaining 0 all the time. There is no reason for EMF to be induced in the circular loop just because there is a current changing in the bigger loop. Why? Because the flux in the circular loop is not changing with time. Flux is remaining 0 at all times through the circular loop, right? So M is 0. Shall we proceed? Now, in an LR circuit, in a typical LR circuit, how does current change with time? I is, say, I naught 1 minus e to power minus t by tau. That's how current grows with time. What is tau? L by R, the time constant of the circuit. Right? What is I naught? Maximum current, which is epsilon by R, that happens at t equal to infinity. Right? Now, if at any given instant the current through the inductor is I, then what's the energy stored in the inductor? half Li squared. Right? We are seeking to trace du dt versus t. We are seeking to trace du dt versus t. Half Li squared means du dt is going to be Li di dt. Li di dt is going to be du dt. That means L I naught 1 minus e to power minus t by tau di dt. Di dt again is I naught by tau e to power minus t by tau, which is like Li naught squared by tau 1 minus e to power minus t by tau into e to power minus t by tau. That's du dt. Yes or no? Li naught squared. Li naught squared by tau. Tau is L by R, etc. Right? Now do you see that at t equal to 0, this will become 0? 1 minus 1. So du dt is 0. At t equal to infinity, this will become 0. That means at t equal to 0 and at t equal to infinity, du dt becomes 0. So one thing for sure, it has to be option A, where at t equal to 0 and at t equal to infinity du dt is becoming 0. Option A, as you can witness, du dt versus t is like this. That's du dt. At t equal to infinity, du dt is becoming 0. At t equal to 0, du dt is becoming 0. Now just, so only option A matches the bill. However, suppose I want to find the maximum du dt. This is du dt maximum rate of change of u with time. How would I find maximum du dt? Okay, yes, one thing, like an idiot, I can differentiate one more time. dtu dt2 equate it to 0 and find the condition so that du dt becomes maximum. But if you are composed and you seek to look at all expressions with love, then you'll realize that it doesn't require all of it. Because to maximize this, look, suppose this is A and this is B. This is A into B has to be maximum. This A into B will always be less than or equal to A plus B by 2 whole squared. Geometric mean less than arithmetic mean. Yes or no? What is A plus B by 2? A plus B by 2 is half. So this will always be less than or equal to 1/4. So what's the maximum du dt? 1/4 Li naught squared by tau is the maximum du dt. That happens when AB becomes 1/4. Right? A plus B by 2. A plus B by 2 is half. You can see that. So AB will always be less than 1/4. Right? So this will always be less than or equal to 1/4 Li naught squared by tau, where tau is L by R, where tau is L by R, etc. That's so maximum du dt. Maximum du dt is 1/4 Li naught squared by tau. Yes or no? Where I naught is epsilon by R, tau is L by R, etc. You can plug in. And when does this become equal to 1/4? When A becomes equal to B. The equality GM will become equal to AM when A will be equal to B. And when does A become equal to B? A becomes equal to B when e to power minus t by tau is half. So then you, by taking the logarithm, you would know the time t when it becomes the maximum. This will give you the time t when it becomes maximum. Got me? So this is the maximum rate of energy transfer. This is the maximum rate of energy transfer to the inductor. Maximum DUD. Maximum rate at which energy is being transferred to the inductor. Clear? We have a certain region of uniform magnetic field, say B. This is a region to the left of this interface. To the left of this interface, we have B going into the plane of the board, right? There is a triangular loop. There is a triangular loop with this being 6 units, this being 6 units, isosceles triangle 5 5, etc. And therefore, realize that this is 3 and this is 4, right? And this loop is being pulled out with a velocity v. This loop is being pulled out with a constant velocity v. Okay, let's see what happens. If it's being pulled out, see, there is flux associated with this loop. B into the area of the loop. B into the area of the loop. What's the initial flux at time t equal to 0? B into half of 6 into 4. The area is realized, half of 6 into 4 is the area of this loop. So which is like 12B Webers is the flux associated with the loop at time t equal to 0. That's the flux going into the plane of the board through this loop. When you pull this loop out, then B remains the same at all points, except that the exposure to B decreases. The area to which that B is exposed is decreasing. Therefore, the flux going into the plane of the board will decrease. Therefore, you would expect an induced EMF. There would be a current driven through the loop, right? So, after a while, let's say t seconds later, say x units of the triangle comes out. X units of the triangle comes out, right? Now B is exposed only to this trapezium, right? So the new flux is going to be, at an instant of time t, is going to be B into this area, which is the area of the bigger triangle, which is 12 square units. Area of the bigger triangle 12 square units minus area of the smaller triangle. See, if x units have moved out, then this would be 6 by 4, this length PQ. PQ from similar triangles is 6 by 4 into x. Do you realize that? 6 by 4 into x, right? That means 3x by 2 is going to be PQ, right? So 12 minus the area of this triangle, which is half of 3x by 2 into x. Right? Half of base, which is 3x by 2 into altitude, which is x. X units is this. This is x units. And this is 6 by 4x. Right? So then, if it's moved with a velocity v, the EMF induced at this instant is going to be d phi dt, right? Which would be like minus 3 by 4 x squared, which is like 2x into dx dt. Dx dt is simply v. V remains constant. Dx dt is simply v. Right? Now, Okay, now the sense of this induced EMF, by the way. Realize that the flux going into is decreasing, so there must be something that would drive flux in. So the induced EMF would want to drive a current this way. This would be the sense, clockwise would be the sense of the induced EMF. If I had said epsilon is minus d phi dt, where on earth would that minus sign give you the direction of the induced EMF? Answer this question to yourself. Right? This or its magnitude will give me the magnitude of the induced EMF, the direction obtained from Lenz's law. Right? Now, what does the problem ask? The variation of power produced in the loop. The resistance of the loop when a current is being driven will be the same, let's say R. So the power would be epsilon squared divided by R. Right? So epsilon squared will be proportional to x squared because v squared is constant. It's moved out with constant velocity. So v squared is constant. So this will be proportional to x squared. Power is proportional to x squared. Yes or no? So power would be some constant times x squared. Power would be some constant times x squared. That means power versus x would be a parabola. Power versus x is going to be a parabola. Is it not? Parabolic variation of power versus x. If you gave it a velocity v and let go the loop, then what would happen is, over a period of time, this velocity will get completely killed. And where will it appear? As Joule heating in the loop. As Joule heating in the loop. But now, what we are doing is, to prevent that killing, an external force is being applied that prevents killing of this velocity. It maintains this velocity so that whatever power is required towards thermal generation is provided by the external agent. The kinetic energy remains virgin, untouched. Right? This is what happens. You know what I'm saying? So that's the job of the external agent. It prevents the kinetic energy from being consumed as thermal energy. You know? If you leave it and let go, then kinetic energy gets consumed as thermal energy, and therefore kinetic energy depletes, will die down. But if you apply a force, then that force will provide enough power so that kinetic energy is not touched. The power that this provides gets consumed in Joule heating. You understand the energy implications of this? Hopefully. Right? Right? Hey, while doing 13, I solved 15 actually. Right? Right then. So, look at these subjective problems independently. You would have attempted some problems from the sheet, MCQs, EMI MCQs, right? But even before I start venturing into the sheet, let me go back to the previous sheet. There were some subjective problems in that sheet. Go back to the previous sheet titled EMI Basics. Sheet titled EMI Basics. Refer to the sheet, please. EMI Basics. And we solved all the MCQs in the last class. Let's quickly look at least some of the subjectives and some electromechanical situations in electrodynamics. All right. So subjective problems, EMI basics. Subjective questions from sheet titled EMI Basics. Right? So, this problem 16, where we have a frame, a horizontal frame like this. ABCD and a rod OQ in this plane, and there is a bulb T. There is a bulb T powered 100 watts, consumes 100 watts, and P is a smooth pulley. This is a smooth pulley and a thread connected to a mass M. And this is known to move down with a constant velocity of 10 meters per second. Known to move down with a constant velocity of 10 meters per second. G is 10 meters per second squared given in the problem. And when this happens, the bulb illuminates at its rated power. The bulb illuminates at its rated power. We want to find the mass of the block. We want to find the mass of the block. Now, realize in this situation, this loses potential energy, right? Just look at the basic energy implication. This loses potential energy. And this loss of potential energy does not manifest as gain of kinetic energy here, because it's moving down with a constant velocity. So the loss of potential energy here would simply get consumed in the bulb, will provide power to the bulb. Now, rate at which potential energy, mgh, the rate at which potential energy is lost is given by ddt of mgh. When it falls through a height h, the loss of potential energy is mgh, and the rate at which it's lost then is mgh dh dt. That's the rate at which potential energy is lost. But dh dt is actually the velocity v of the mass, is actually the velocity v of the mass. So this is like mgv, this is like mgv, right? So mg into the velocity of the mass is the rate at which it loses potential energy. That means this is the power lost, this is the power loss, gravitational power, right? And where will it appear? The rate at which potential energy is lost, that means these many watts will simply appear as 100 watts of the bulb, will appear as 100 watts of the bulb, that far and no further. That's the physics of the situation. So then V is known, G is 10, you'll be able to calculate M, 10, 10, 100, so M is 1 kg. The mass is 1 kg, this mass is a kg. As simple as this. Isn't it? Sounds good? Alright, let's look at the next one. 17. Let's look at 17. Are you all there with me on this? No confusion, right? Simple energy implication. Okay, this is the situation. We have a capacitor C and there is a connector which could move down under gravity, influence of gravity, and there is a uniform magnetic field B naught. We'll assume that it's going into the plane of the board. And this Mn and Pq, Mn and Pq are vertical smooth conducting rails. The connecting rod is of length L and has a resistance R. So we can put the resistance here as if it's separate. This has length L and resistance R, and say mass M. The mass of this rail is M. Okay. The capacitance is C. We want to find what happens. We want to find the maximum current that could be produced in the circuit. Okay. See, at time t equal to 0, it's at rest, isn't it? When it's at rest, there is no motional EMF generated. Let's say, let me call this TL. Let me call this TL. Okay. There is no induced EMF in this rod TL because no velocity. It's moving past a magnetic field. But initially it's at rest. It has an acceleration g downwards, but it has no velocity. So there is no motional EMF. If there is no motional EMF, there would be no charge associated with this. There would be no current associated with this. Clear? Okay. Next, it starts to move down under the influence of gravity. It starts to move. So it develops velocity. While it develops velocity, there is motional EMF generated, right? Which drives a current through this, which develops charge on the capacitor. That is what happens, isn't it? Okay. Two aspects of the problem, an electrical aspect and a mechanical aspect, right? At a certain instant of time t, say, it has a velocity v downwards. The rod has a velocity v downwards, right? Then, do you realize that it will serve as a seat of EMF, epsa equal to BVL, this way? I hope you realize why this sense, because V is like this, B is like this, so V cross B would be like this. So this would be connected to the positive terminal, this would be connected to the negative terminal of the battery, right? Now at this instant, let's say the current is I. Let's say the current is I. And the charge on the plates of the capacitor is Qn minus Q. Now, in the electrical domain then, if I have to apply KVL to the loop, then realize that IR is the drop across this, Q by C is the drop across this, then going this way, minus epsa is the drop across this. All of this must add up to 0. So when I apply KVL to this loop at an instant of time t, Q by C plus IR equals BVL. How about it? That's the electrical aspect of the problem. That's the electrical aspect of the problem. There is then a mechanical aspect of the problem. There is then a mechanical aspect of the problem. As far as the mechanical aspect of the problem is concerned, realize that this TL at this instant of time, just to draw it separately, has a velocity v downwards. There is a current associated with it, I. So this is now a current carrying conductor in a magnetic field. It will experience a magnetic force dl cross b, dl b. So it will experience a force upwards, right? Most of the time I don't even justify upwards because I know it has to oppose the cause. The cause is downward motion, that has to be opposed. So I know that it's going to be upwards. I don't have to do a dl cross b all the time to figure that out, right? So it experiences a force BIL upwards, the magnetic force BIL upwards, right? And there is also a force due to gravity. And at this instant, it has a velocity which is changing with time, right? So can I apply Newton's second law to this, right? So that would be the mechanical aspect of the problem. This is the electrical aspect. Now let's put the mechanical aspect of the problem in perspective, right? So the mechanical aspect of the problem is applying Newton's second law, mg minus BIL is m dv dt. What about this? Sounds good, no? Now, I need to find I max. Given this, this is the physics of the problem. Now the next thing is just the mathematics. All right? There is no more than this in as far as physics is concerned. The mathematics of the problem. I want to find I equal to I max. I want to find I equal to I max. Now, one thing, when I is I max, di dt must be 0, isn't it? When I is I max, di dt must be 0, isn't it? For I equal to I max, di dt is 0. For I equal to I max, di dt is 0. Clear? So we need to bring a di dt somewhere, right? We also don't want q to stay. So I would like to differentiate one with respect to time, in which a twofold advantage, a di dt will appear and dq dt will become I. So I want to deal with I. Yes or no? So it would be a good idea to differentiate equation 1, where I can bring in a di dt and I can dispense away q, because dq dt will then turn out to be I. Very good. So if I differentiate one with respect to time, I am differentiating this equation with respect to time. This will become I by c, because dq dt by c, I by c, plus r di dt will be bl dv dt. That would be the equation when I differentiate this with respect to time. So I get like a I by c plus r di dt equals bl dv dt. Yes or no? Now, when I is I max, di dt will become 0. So I'll be able to find I max in terms of dv dt in the first place, right? So for I equal to I max, di dt is 0. So if this is 0, when this turns out to be 0, then this I will be I max. Then this I will be I max, right? So let me put di dt 0 and solve for this I. So then this I, which is I max, is, when di dt is 0, is like a blc dv dt. Yes or no? Right? So now dv dt is something that I don't want, but I want I. So in this, I can replace this dv dt, in the mechanical aspect of the problem. This dv dt could be replaced by I, which is I max, by blc, isn't it? Then I can solve for I. The I that I obtain will be I max. So this dv dt I can replace by I by blc, right? So m I by blc is the dv dt, right? This dv dt I obtain from here, I by blc, and I plug into this. Then this I that I obtain from this equation would be I max, clear? So we have like I into m plus bl by, I'm sorry, m by blc equals mg, right? I'm sorry, I'll just fix this. mg, see, I transpose this, so I into bl plus m by blc is mg, then this I would be I max. So I max, which is this I, is mg blc by b squared l squared c plus m. This would be I max. This is going to be I max. Right? Just to give you an electromechanical situation in which an inductor is involved. Just let me take a detour from this. So you got this, right? Is there a problem with what I wrote? No? If you allow me to wipe this off then, right? Let me take an electromechanical situation in which there is an inductor. This is a rod. This rod is of length L and mass m, and it's given an initial velocity u, and there is this region of uniform magnetic field B plunging into inductor L, resistance R, and there is no current in the inductor initially. We want to find the charge flown through the inductor. By the time the inductor current in the inductor becomes I, the velocity of the rod becomes v1, and the rod has traveled a distance x. So this is, say, time t equal to 0. T seconds later, say the inductor acquires a velocity v, right? Now if it acquires a velocity v, there is going to be an induced EMF in this sense, where epsi is BVL, which through this will drive a current I. This current I comes to this junction and gets bifurcated. A current I1 flows through the inductor element, a current I2 flows through the resistor. But the drop here BVL will be the same as the drop here. The drop here will be L di1 dt. The drop here would be I2R, right? So BVL will be equal to the drop across the inductor element, which is L di1 dt, and will also be equal to the drop across the resistor, which is in parallel, I2R. Yes or no? Right? The force acting on this, BIL, that's all, nothing else, right? Now m dv dt represents the force acting on it, and this must be minus BIL. This must be minus BIL. Right? What we do here is, this I can write as I1 plus I2. This I can write as I1 plus I2. So m dv dt is minus BL I1 plus I2. Or m dv is minus BL I1 dt plus I2 dt. Yes or no? This I can write as minus BL I1 dt plus this I2 I can write as BVL by capital R. This I2 I can write as BVL by capital R. Yes or no? Now if I integrate now m dv, v was initially u, to velocity becoming v1, as the problem says, is minus BL. Now when I integrate I1 dt, I'll get the charge that flows through the inductor element. I1 is a function of time, and when I integrate I1 dt, I'll get the charge q flowing through the inductor, right, till that time, plus BL by R. If I integrate V dt, I get the displacement of the connector, yes or no? If I integrate V dt from t equal to 0 to that instant of time, I'll get the distance traveled, in this case the displacement x of the element, right? So integral V dt will give me the displacement x, and the left hand side is m into V1 minus u is the left hand side, the right hand side, and you can solve for q. You can solve for q, the charge flowing through the inductor element.